Continuous is like a dimmer switch, not just on and off. Values can land anywhere in a range, so we talk about ranges, not one exact number. Heights and weights often make a bell-shaped histogram. One central bump, fairly even sides, and gentle tails. Quick check. If it looks like a camel with two humps, bimodal, or a ski slope with a long tail, skewed, the normal model is probably not the hero today. Quick eyeball test. Does the histogram look like one smooth hill with left and right sides that are mirror-ish and gentle tails? That's normal. Red flags are a camel with two humps, a shark fin with heavy skew, or chunky tails with lots of outliers. Classic normalish examples: adult heights in one group, small measurement errors around 0, steady factory dimensions, and big scores built from many small influences like combined tests. Bottom line: smooth, single peak and symmetry says yes. Lumpy or lopsided says try a different model. Meet the bell curve, aka the Gaussian model, named after Carl Friedrich Gauss, who used this function as a law of errors and made it famous. It's perfectly symmetric. Mean, median, and mode all sit in the center. The total area is 1, so half the data lives left of center and half right. That scary formula on the slide is just the recipe for this shape. You don't have to memorize it, just remember who to thank or blame. Gauss, along with a bunch of other nerds such as Abraham de Moivre and Pierre-Simon Laplace. You might be fascinated by the appearance of two celebrities in this formula. Why do both E and pi show up here? E is there because the bell curve uses exponential decay. Pi arrives when we force the total area to be 1. Bottom line: E shapes the bell. Pi scales it so the area is exactly 1. A mathematical duet masterpiece, emphasizing their mysterious connection. Think of mu and sigma as two knobs. Mu is the where knob. It slides the bell left or right. Sigma is the how wide knob. Small sigma makes a tall, skinny bell, low variation. Big sigma makes a wide, chill bell, high variation. Together they can match the curve to any bell-shaped data. Mu is approximated by the sample mean and sigma is approximated by the sample standard deviation. In continuous land, a single point has no chance. It's like trying to pause a video at exactly 42.000000 seconds. Nice idea, zero chance. So the probability that x equals exactly a is 0. What matters are ranges. Any range around a has some chance, but the single point does not. Bottom line: points are labels. Intervals carry the weight. Empirical rule says about 2/3 of the data live within mu plus or minus 1 sigma, about 19 out of 20 within 2 sigmas, and basically everyone except the statistical weirdos within 3. If your normal data has tons of points beyond 2 or 3 sigmas, that bell isn't normal. It's ringing the drama alarm. Think of 1 sigma as the comfy neighborhood, 2 sigmas as the suburbs, 3 sigmas as the edge of town. Out of pure intellectual gold, legends of mathematics forged a sacred bell that became the pinnacle of statistical wisdom. To build this marvel, they summoned 2 grand masters, E to shape how chances fade at extremes, and pi to maintain the unity of total probability. Through the mysterious connections of these two irrational numbers, noise finds a beautifully rational shape, and we find perspective.